Cool. Hello everyone. My name is Rupanshu. I am a CS-PhD student at Stanford University. This is joint work with Benjamin Driscoll, Wang, and my advisor Alex Aiken. So this talk is called Incremental Equality Saturation, but what I'm really here to tell you is that you should stop throwing away your EGRAPHS. What do I mean by that? Well, if you look at the way many EGSAT projects are structured, it's roughly like this. The input term is inserted into an empty eGraph, EGSAT is run, and an optimized term is extracted. And this pipeline is run afresh for every term. This means that equalities that are discovered during EGSAT for one term are not retained while optimizing the next one. They must be rediscovered. If the terms we are optimizing are similar to each other, not sharing equalities across them means we are potentially leaving a lot of performance on the table. And indeed, we are not the first to make this observation. The Egg paper made essentially the same observation and introduced batched EGSAT as a way of obtaining this kind of sharing. In batched EGSAT, all terms are taken together. They're added to an empty eGraph, EGSAT is run, and optimized variants of each term are extracted. This results in significant improvement in performance as sharing between terms is discovered by the eGraph before any rewriting is done. But the central limitation of batched EGSAT is that it requires all terms to be available simultaneously. This is not true in any application with user interaction, as in any such application, there will be a delay as the user provides successive terms. Most compilers fall in this category. So the question is how to share equalities across terms that are only available at different points in time. One idea is to use the same eGraph for every term. Here's how that would work. We optimize the first term normally, but we persist the eGraph that is obtained at the end. Then, instead of adding the next term to an empty eGraph, we add it to the persisted eGraph, and so on. This also does not work, mainly because the current term is often disjoint with most of the eGraph. Let's see the problem in more detail. Say I have this big eGraph containing various terms and their equalities. Say the kth term I want to optimize is f of x. We insert f of x into this eGraph and obtain something like this. The problem is when we run EGSAT, the algorithm will try applying rewrites to the entire eGraph, when we only care about applying rewrites to two E-classes, the one containing f and the one containing x. The problem is exacerbated if the other E-classes are not already saturated, and I will discuss later that this is often the case. So to summarize, the central issue with utilizing standard or batched EGSAT for settings where terms are available at different points in time is that both algorithms lack a notion of current term. And this is exactly what incremental EGSAT provides. If you remember one thing from this talk, remember that incremental EGSAT extends standard EGSAT with a notion of current term, so that rewriting is focused on the part of the eGraph that is relevant to the current term. Let's look at the algorithm in more detail. We're going to consider a sequence or stream of terms T0, T1, and so on, where we must accept each term, optimize it, and return the result before seeing the next one. The rest of the setup should be familiar. We have a rewrite set, a budget, which can be a maximum number of e-nodes to add, a number of iterations or a time limit, and a cost function, which is used to select the final optimized term. Let's look at a concrete example, an algebraic simplifier. We will consider a sequence of two functions of x. The first one is x to the power 0. The second one is the derivative with respect to x of x times 1. We have some algebraic rules. For example, the first one says that anything to the power of 0 is 1. The second says that the derivative of anything with respect to itself is 1, and so on. Our budget will be a maximum number of e-nodes, and our cost function will just be size. So we're going to try to minimize the size of our input terms. So we take the first term, we add it to an empty eGraph. This is what it looks like. We do standard EGSAT, and we obtain an eGraph like so. I flattened some e-nodes to simplify these diagrams. Note that we discovered that x to the power of 0 is 1. Next, we do the same thing for our second input term. We add it to an empty eGraph, run EGSAT, we get something like this. Note that the second x's E-class is the same as the previous term, but all these equalities had to be rediscovered by the algorithm. Now let's do the same example with incremental EGSAT. For that, I have to tell you about incremental eGraphs, which are the underlying data structure for our algorithm. An incremental eGraph is just a standard eGraph plus versions. There is a version for each E-class and a current or latest version, which is a global variable. There is an additional component that I will motivate in a few slides. Okay, we begin by setting our current version to 0. We add our first term to the incremental E-graph. It looks the same, except now every E-class has a version assigned to it. After incremental EXAT, we obtain the same set of equalities as before. Now, before adding the second term, we increment a global version to 1. After we add the term, we have something like this. Notice that the new E-class gets the latest version, the others remain at 0. And when we do incremental EXAT, the algorithm only applies rewrites to the part of the E-graph that is new. And at the end, we obtain something like this. No more rewrites can be applied at this point, since there are no E-classes left with the latest version. So I just mentioned that rewrites are only applied to the part of the E-graph that is new. Let's make that more concrete. If we have a rewrite rule with this left-hand side, then the rule in incremental EXAT is that the top symbol must match in an E-class with the latest version. And we impose no additional restrictions on pattern variables, except they form a valid E-match according to standard EXAT. There is one more restriction on E-matching that I will tell you in a few slides. Okay, so we saw how incremental EXAT uses versions to keep track of the current term and how versions integrate with E-matching. However, it turns out that versions alone are insufficient for making incremental EXAT practical. The problem is due to non-termination of EXAT. This unfortunately happens to be very common. Indeed, EXAT over all the rewrite sets we tried seem to be non-terminate. Non-termination, coupled with using the same incremental E-graph for optimizing many terms, leads to what we call the runaway E-class problem. To explain, consider a really big E-class containing hundreds or thousands of E-nodes. Say we order these E-nodes by cost. Consider a parent of this E-class which we want to rewrite. There are many candidates for rewriting. What happens in the runaway E-class problem is that EXAT squanders its entire budget rewriting terms that do not lead to a global or local optima, and the algorithm's ability to optimize severely deteriorates. How do we deal with this issue? Well, our insight was that f of E1, which is the lowest cost E-node in this E-class, is likely to be a much better candidate for rewriting than f of En, which is the highest cost E-node. And this is exactly the motivation for the second component of incremental E-graphs. It is a top K analysis. So if we go back to our big E-class from before, top K works by attaching an additional piece of information to it called the top K set. If we set K to 2, then we're going to track all E-nodes with the lowest and second lowest cost in this E-class. And K is equal to 2 is indeed the value we use in our experiments. With that, I can state for you now exactly how E-matching works in incremental EXAT. If you have a rewrite rule with the left-hand side like this, as before, the top symbol must match to an E-class with the latest version. And as before, there are no additional restrictions or inner pattern variables, but we impose a restriction on any inner symbols. If they match an old E-node E, then E must be in the top K set for its E-class. This restriction lets us focus our budget on terms that are likely to lead to a better final solution. Before moving on, I want to note that top K is largely orthogonal to incrementality, but it was required to deal with the runaway E-class problem. We could not obtain good performance of incremental EXAT without top K, and it could potentially be used in standard EXAT as well, although we have not tried. Okay, now I'd like to step back and discuss some higher level properties of this algorithm. First, is incremental EXAT even sound? Well, incremental EXAT cannot find incorrect inequalities, as the set of equalities valid under incremental EXAT is just a subset of those valid under standard EXAT at any point. But it's also interesting to consider the relationship between the set of equalities found by the two algorithms. The general situation is best represented like this. There is a big intersection indicating that there is a large number of equalities that are found by both algorithms. Then there is a set of equalities that incremental finds that standard does not find. This is expected as incremental EXAT has access to more information. However, there is also a set of equalities that standard finds that incremental does not find. I want to explain why this is the case. Let me preface the discussion by reminding you that we're assuming that EXAT over our rewrite set does not terminate, which to the best of our knowledge happens to be the most common case in practice. Okay, so why might incremental EXAT miss equalities that standard EXAT is able to find? Consider a really big incremental E-graph that we have obtained after optimizing 100 terms. We increment our current version to 100. Now we have this new term, f of x, and we want to add it to this incremental E-graph so that we can optimize it. Well, to do that, I must pick a version for each E-class in this term. We basically have two choices. If I pick 100, that means I've chosen to activate both E-classes for rewriting. If I pick anything less than 100, then I've chosen to disable these E-classes for rewriting as per the semantics of E-matching. The problem is just that any time you choose to disable a subterm for rewriting, you might render an equality unreachable that is otherwise reachable by standard EGSAT. And you have to disable subterms for rewriting sometimes, because otherwise you're not getting anything from incrementality at all. So keeping in mind that no reasonable policy for picking versions can guarantee that incremental EGSAT finds every equality that standard EGSAT can find, our job with designing a policy is easier. It is just to obtain good performance. The policy we actually use in incremental EGSAT can be explained based on a well-exploredness heuristic. It says that every old E-class with at least m E-nodes is well explored, so don't explore it ever again. In practice, we set m equals 2. So let's see what our policy entails on the previous example. So we have this incremental E-graph and we're inserting this new term into it. The policy just says that if the E-class that f goes into already has at least 2 E-nodes, then you don't do rewriting on it. And otherwise you do, and the same thing here. This well-exploredness heuristic can also be used to explain the rule for merging of versions. So you have 2 E-classes, they have different versions, and you applied a rewrite rule that merges the 2 of them. In our design, we give the resultant E-class the lower version. And the rationale is just that, for example here, f is considered to be well explored after the merge because it is now equal to E-nodes that were already well explored. I want to stress that the design decisions we've made for incremental EGSAT, the well-exploredness heuristic, the rule for decrementing versions, only make sense when EGSAT is non-terminating. There exists an alternative design of incremental EGSAT that is suitable when EGSAT is terminating, that enjoys the property of always finding a superset of equalities of standard EGSAT. And in that design, versions would only increase, never decrease. And in that design, top k would be unnecessary as long as you always ran to saturation. However, we just couldn't find any rewrite sets for which EGSAT was terminating, and so this design was never implemented. Okay, with that, let's look at some performance results. After all, the whole point of incremental EGSAT is to improve performance. We'll use our running example, the algebraic simplifier. We randomly generate 1,000 functions of x of a given size. Our budget will be a maximum number of E-nodes to add. The cost function will try to remove derivatives and integrals while minimizing size. This is just taken from the math example in EGG actually. And we will compare standard and incremental EGSAT in terms of total cost for the 1,000 extracted terms versus total time. Here are results for 1,000 terms of 2 different sizes, 11 and 13. Total cost is on the y-axis and total time on the x-axis. Each point here corresponds to a full run of 1,000 terms with a specific node limit. We see that as we increase the node limit, incremental EGSAT quickly becomes Pareto optimal over standard EGSAT in these 2 metrics. And for larger terms, we see that we need a larger budget before incremental EGSAT becomes Pareto optimal. Here are some detailed results for optimizing 1,000 terms of size 11 with a specific budget, in this case 6,400 E-nodes. Incremental EGSAT is about 3 times faster, and it finds solutions of lower overall cost. However, incremental EGSAT does not find an equivalent or better solution than standard EGSAT for every term. For the vast majority of terms, the 2 algorithms find a solution of equal cost. However, for 40 terms out of 1,000, standard EGSAT manages to find a better solution. This is just due to the problem we discussed earlier, where the sets of equalities the 2 algorithms find are not exactly the same. To conclude, I have presented a new algorithm for EGSAT that is able to reuse discovered equalities across terms that are temporally separated. The main limitation of the algorithm right now is its requirement of a local cost function. as that is required to even define what top k is. Non-local cost functions include, for example, if you want to solve an integer linear programming problem over the eGraph. Such cost functions are used in several projects, and relaxing this requirement is ongoing work. I'm also looking for more applications for incremental EGRAPHS, so if you have something in mind, please come say hi. Thanks for listening. This is the link to our abstract, and I'll be happy to answer any questions.
Thanks for the great talk. Okay, here we go. We have got some questions, and we have plenty of time for questions.
Hey, thanks for the great talk. This is Rajat from MIT Engine Street. So for your top K heuristic, this is probably not true, but is it equivalent to essentially pruning to the size that you select, or no?
It's not, because top K only kicks in when you have an E-class that is old. If you have, so if you take a new term and you start doing exat on it, top K doesn't kick in at all. It's only when the new term shares something with an old term that top K kicks in, and it tells you, well, don't do rewriting on the old part because you probably already did it. And also, it's not equivalent to pruning in another sense, in that you can still get hash consent for e-nodes that are not top K. So if you have your E-class, it has some top K set. Consider some e-node that is not in the top K. You can still hash cons into that e-node, and that can still give you some share.
Thank you.
Yeah, thank you for the great talk. So just a simple, I guess, implementation question on top K. How are you determining the cost? Is it like you're running a cost function every time, or are you like propagating some data analysis throughout the eGraph? Yeah.
Yeah, so the good thing about local cost functions is that you can just implement them as an analysis. So it's just an analysis, basically.
Okay. Yeah, and I guess the future work is looking to getting a more global cost function there?
Yeah, I think for that you would need a local proxy to define top K, and then at the end you could do your global function, something like that.
Okay, cool. Thank you.
Hey, thanks for the great talk. Yeah, one question about applications. So I was wondering, like, in my head, typically, equality iteration is kind of one input program that you want to optimize, like a compiler, and then you get one output. So you were thinking of a kind of a sequence of inputs that have some overlap. And I was wondering, like, what applications do you have in mind that have kind of the sequence as a typical input kind of?
Yeah, thanks for that question. Well, just think of a compiler, you know, you like write your program, you compile it, then you make some change to the program, then you want to compile it again, maybe you want to compile the program tomorrow. It's a sequence, like, because you're running the compiler multiple times, and so the inputs naturally form a sequence. Like, the only program that wouldn't have a sequence is a program that was only run once, you know.
Hi, thanks for the presentation. One question I had was, does the order in which you add the terms to the equality iteration matter? Do you have experimental data from this? As in, it's because you're kind of introducing a phase ordering in which terms get explored first, second, and I think later terms can benefit a lot from the earlier terms, whereas the earlier terms are like.
Yeah, so this is true, but the model in which this is operating is that, like, I don't have any control over the inputs I'm receiving. Like, my perspective is that I am this optimizer, the user sends me terms, my job is to optimize them, so I don't really have an axis along which I can, like, reorder terms.
Sorry. The question was, have you tried playing around with switching up the order, and have you seen like improvements or degradations in performance of the extracted terms?
So I don't have results for exactly the experiment you're suggesting. In this case, these terms are randomly generated. But I think if you like do some pathological case where you switch around terms, you can get differences in performance, definitely. And in fact, for later terms, like sometimes later terms will get saturated much more quickly because they have a lot of information already there.
Have you thought about how this would work with Eglog? Do you see any challenge for integrating like versioning into Eglog?
So that's a great question. This implementation is just a fork of Egg, so this is not for Eglog. I think Eglog is going to have a lot of the same problems, like top K. If you want to do something like this for Eglog, you're going to have something like top K, because the runaway E-class problem where E-class is just like explode with useless E nodes, that's going to occur. Versions, I think you could just implement straightforwardly. Some of the other details might be different. For example, this implementation has a special implementation of rebuilding, which is incremental. The standard implementation in Egg is not incremental. So I think that you would have to modify for this to work for Egglog.
Hey there, great talk. Thank you so much. I'm curious, along the lines of this question, if you've thought about how this relates to semi-naive evaluation and something like Datalog or Egglog. It seems like there could be some cool overlap there.
Right. So I think this is largely complementary to semi-naive evaluation. My understanding is semi-naive is just an optimization for E-matching. And in incremental EXAT, you basically only E-match over the part of the E-graph that is new. So like that's all, like I don't think you can optimize it further because like you have to match over the part that is new anyway. So my understanding is that this is complementary.
I have a question. I really do like this work because it's a very practical sort of motivation. You're willing to sacrifice completeness because we've already sacrificed it, right? It was never terminating to begin with. And we're sort of making these trade-offs of like, well, we'll give up a little bit of completeness there because it buys us more completeness in this direction because we now have more time space or whatever. And it seems like the main tool you're using here is this like very granular approach, which you both are using to get this top K and the incremental approach, which is like we're no longer treating all members of the E-class the same, right?
Yes.
We're sort of discriminating between
Yes.
them, saying you can look at these but not those at different times and so on. I think this is very powerful and probably a very necessary tool to like reach scalability, especially in this sort of incremental setting. But I also think that it sounds like we're opening Pandora's box, right? Like now we have so more knobs and knobs on knobs, and like you can imagine, you know, introducing, you're already bringing in sort of cost information to sort of steering the search. So I don't know, how do you sort of square that circle? How do you think about, you know, controlling the complexity of controlling the search?
Yeah, that's a great question, and this was like a major tension while I was doing this project. So before we had top K, like this would not work at all. Like performance was completely terrible. Basically what would happen is after you had optimized a few terms, the E-graph was like so big and full of like useless equalities that nothing would happen. You would, if you gave it a budget of like 5,000 E-nodes, it would just like create 5,000 useless E-nodes and finish. And so it's just that because EXAT is non-terminating, you have to have some sort of guidance to hope to get useful things out of really big E-graphs. And you need not be incremental. Like if you just think about doing one run of equality saturation, but with a humongous E-node limit, like the only way to get a benefit out of that is to have some guidance while you're doing it. Otherwise, like you will get the best thing in like the first 10% of the search, and the rest 90% will be like nothing.
Okay, let's think this through one more time.